James O'Donnell from UCD. I'm joined here by Lewis from NUIG, who's also representing Dr. Marcus Keane. So slight change of track here today for this particular presentation. It's a research-based initiative and it's applied research. So what we're hoping to do is to have the outputs of this particular project be usable for industry in general and those that focus on energy modelling. So essentially we want to take existing information in building information models and convert that to a semi-automated process into a building energy model. And our target in this particular case is the Energy Plus simulation engine. So our project team for this particular undertaking included myself. I have about 15 years in the BIM area, and particularly BIM for energy modelling domain. Marcus and Lewis focus on HVAC modelling and advanced energy simulation modelling, particularly using Modelica at this point. Our industry partner is Zutec, and Zutec provide an information service for the construction industry, particularly for new buildings. And Zutec have a database platform which is essentially a multi-model that allows projects to store their information. Zutec will then manage their information, organize that information, and make it reusable for other purposes. So it's a platform that enables additional services. And the whole idea with this particular project, as it's funded by Enterprise Ireland, is we wanted to create a new market for BIM2BEM based solutions, and for this market to be available to all industry and anybody who's interested in this particular domain. And Zutec will also use the service as part of their own offering. So, as mentioned, the market at the moment is currently lacking a robust tool that will actually convert BIM for energy modelling. Particularly the geometry has been traditionally a key weakness in this area. Furthermore, I would say the two categories of problem that we encounter. First of all, there's an inconsistent approach to modelling of geometry in BIM-based CAD environments. And the second issue, which is crucial, is that the quality and consistency of CAD export, that's the model that's been exported, doesn't necessarily align with some of the very sophisticated tools that are available. And those types of tools are developed by academic institutions such as the Lawrence Berkeley National Lab. I was part of the team that developed a project similar to this when I was in the US. And that particular tool is just very sensitive to inputs. And in the real world, the high quality inputs that are required just simply are not available today. So it's a distinct market gap that Zutec wanted to exploit and Zutec wanted to pursue. So key issue I want to point out here as well is that what we want to do is to be able to remove the manual effort associated with generating energy models. And that's a cost, and it's an unnecessary cost, in my opinion, for these types of projects. Okay, so the key goal here, I have a couple of words here highlighted in bold, and it's a practical and sufficiently accurate solution. So this is not a perfect solution. What we want to do is to be able to enable a solution that is widely available and easy to use. So the emphasis on practicality, and we will incrementally increase the accuracy of the solution thereafter. So has anybody here heard of a space boundary or an IFC space boundary? Okay, a handful of people. Okay. But what that actually means is that BIM typically contains very detailed representation of a building, whereas the energy model in question typically contains a very simplified representation of the same building. So space boundary for a room like this, we have one encompassing space boundary. That's called a first level space boundary. But for heat transfer purposes, we're looking at heat transfer that is orthogonal or normal to a particular plane. So from inside to outside in this case, just taking this wall in question, we have a window here. That's a second level space boundary. We have another second level space boundary on this side. This column creates all sorts of issues for heat transfer purposes. Remember, heat transfer is in this direction only. And we have the column, which is fine, so the space boundary, space boundary, space boundary. But also this column is in space, protrudes into the space. That creates complications for heat transfer that's supposed to be only in this direction. So it is a complex issue going from that detailed BIM representation to the energy model representation. As a result of this project, we want to have two core components. First one is naturally geometry related, and The second one is HVAC related, and Lewis will talk about that. So as I mentioned, the project aims are essentially to enable a system that's quick and easy to use based on a cloud-based infrastructure. Okay. So where are we starting from? First and foremost, we have our traditional workflow where we have a number of different data silos of information, for example, the architect, structural engineer, mechanical engineer, etc. And this information is available, but not necessarily reused through intelligent or semantic means. So what actually happens in practice is we have this building energy modeling component, I'll leave that alone, just here up the top, and the actual energy modeler redesigns the building in the actual modeling tool. So it takes unnecessary effort, it's error prone, it's timely, it's time consuming, and it's costly. Whereas, and there's no round trip really between the energy model itself, in Energy Plus format, and BIM or any other digital multi-model environment. Okay, instead we proposed the BIM2BEM workflow, which essentially reuses the information currently available in BIM. And that may take a little bit of rework on the side of the BIM. If you have an architectural model, it might need a slight modification for energy purposes. An architectural representation of a space is not necessarily the same as a thermal representation of a space. So the idea is with this particular approach that we import the BIM, typically in IFC format, and that's been a huge issue. It took us quite a bit of playing around. One of our speakers this morning mentioned that they had to learn on the job in terms of what particular tool chain worked for their processes and their needs. And we actually went through a whole range of Autodesk Revit and ArchiCAD plugins in terms of what export functionality supported the process. And we found something that worked with Revit in this case. So that information is uploaded to the Zootech platform, and from there, Zootech are also in a very unique position for this project. They have a lot of experience, a lot of information stored from previous projects, and they have the ability to create templates of constructions for walls and windows, etc., say for office buildings or for hospital buildings, etc., based on their previous experience. And that information can complement existing information from the left-hand side bin here. So the project runs through a semi-automated process and runs through a set of what we have here, BIM2BEM algorithms for geometry and HVAC, and I'll now talk a little bit about the overall project and the geometry algorithms. So naturally, as you might imagine, the process is split into two work packages, the geometry component and the HVAC component, and the outputs are then combined prior to the simulation run in the Energy Plus tool. Okay, so just a couple more slides on the geometry before I hand over to Lewis. So I mentioned those space boundaries a minute ago. So typically what the industry has looked for is the space boundaries are contained within the IFC file. Instead we said, let's go back to basics here, and what's the common denominator for an energy model. So the basic unit or the basic object or component in an energy model is actually a zone. So we said what we wanted were a clean definition of zones only, and with the accompanying walls, floors, windows, etc. And we would basically generate our own space boundaries in memory and transform those space boundaries into heat transfer surfaces for the energy model. So I've given an example here of just a heat transfer surface up on the top left in the case where the zone is actually removed, the second image. Okay, we encounter a number of different problems. The first one is holes in particular surfaces. If we look at this particular algorithm 2 case, we see that if that was in elevation or cross-section, those holes would probably represent windows or perhaps even doors if they extended to the bottom. And that's not an issue. But where we have the problem is if this particular representation is in plan view and those holes are in horizontal surfaces. And this creates all sorts of problems for the Energy Plus engine. So instead of having one slab with 3 holes, we need to decompose that slab into a number of rectangular or triangular surfaces. We've gone with rectangular because it's easy for debugging purposes. Okay, so that's just 2 components to this. And I just want to say that when I started in 2001 in the BIM2BEM area, a lot of engineers had tried to take on this project. And as engineers, we kind of fancy ourselves in terms of Cartesian geometry experience, and we'd say, yeah, we can do this. But these particular problems, when you actually break it down and deal with the level of complexity in buildings, it required a graph theory-based solution from computer science to actually solve this problem when you're looking at buildings of scale. So please keep that in mind. This is not a trivial solution. Okay, I also wanted to highlight the third component of our algorithm, and that is it just addresses columns and spaces. So I mentioned the zone is a fundamental component of an energy model. If we remove this particular column from the energy model representation, we need to account for the zone volume accordingly, and that needs to be done carefully and subtracted from the new volume if this particular column is in question. Okay, so one key issue in future work in this particular area is plenum spaces, and that is a real issue. The definition of plenum spaces as zones or maybe not, depending on a given project. So in addition to the algorithm, we've also provided a list of guidelines for for energy modelers using the ZooTech platform. I'll now hand you over to Lewis.
Hi, I'm Lewis from NUG. I'm going to present how we envision the HVAC generation tool. So what we have seen so far is the geometry transformation. This is the first part of the application. The second part is is to provide a practitioner or a user with an easy way of assigning the most typical HVAC systems to a set of zones, a set of thermal zones that previously the UCD engine has matched and has simplified. So a typical user would load the file handed, and then assign in very simplistic way, following a number of pre-populated templates, the most typical HVAC systems. So what's the idea here? The idea is to avoid what's the main barrier to adoption of energy modeling, which is time-consuming assignment of HVAC system templates, control algorithm by providing a set of pre-populated templates. So we are avoiding any kind of subjective judgment and any kind of manipulation of inputs, which is one of the most important things to adopt energy simulation. So what we have here is two screenshots of the graphical user interface. So we launch this, and we just have to focus on which zones are served by any particular. So at the higher level, how many plant level rooms are, so how many cool water, hot water generation do we have? Then at the zone level, how many air handling units do we have? We have identified the most typical HVAC systems. So whereas it is a constant volume, variable L volume, fine coil units, or variable refrigerant flow. And then if there is any zonal support system, like reheating coil and things like that. But this is all provided by the pre-populated templates. So what we want here is just to hand a bunch of zones that come from the geometry, and then quickly assign HVAC systems with a minimum knowledge. Okay. So once we've done this, we can swap to another tab where we can also extract a bunch of zones, classify by floors or by uses, and then assign pre-populated templates with typical plug loads, lighting loads, schedules, and so on. So once we've done that, we can run the simulation engine, and we can generate Energy Plus files, and we can run the Energy Plus files. So as James pointed out, this is not a detailed Energy Plus simulation. So there's a lot of input that is being pre-decided. But then there is the opportunity of generating lots of Energy Plus simulation in a very quick and a very straightforward way. Okay. We have a number of test cases. I think we're running out of time. This is just to show you the industry scale test case with more than 200 zones. So with this test case, we are able to launch the geometry mapping algorithm, identify more than 200, 300 zones. Some of the zones, they are probably irrelevant for energy modeling. Some of the interstitial spaces, some of the ancillary spaces. So, for instance, we are able to identify 32 rooms, 32 toilet rooms, and the common areas, and assign a HVAC system to them. Forget about the very less detailed rooms, and generate an energy simulation in very quickly and very straightforward manner. Okay. I don't know, James, if you want to summarize this. This is kind of the future plans for.
Okay, so to wrap up, we have taken this approach. We've worked with a couple of companies, and we're looking for other research opportunities that you guys in industry would like to pursue, and particularly in the area of, say, national funding and European funding projects. Okay.
Okay.
Thank you very much.
Thank you.